to announce Arun Sharma and Eric Matin, who's a senior lecturer both from University of New South Wales, and they will be talking about something which is probably a bit different from what you've been hearing all the time throughout this machine learning school. And in this case, it's how to probably crossbreed machine learning and logic. And so I hope you'll enjoy this lecture. And Arun is the first one to speak.
Thank you, Alex. So what do I do?
Okay, just put it in your pocket. Just put it somewhere.
I'll just put it.
Yeah, wherever you feel most comfortable.
Okay. Okay. Thank you for actually inviting me. It's a pleasure to be here and participate in the machine learning workshop in the summer school. Eric will be giving the second part of the talk. And this is a work that we have been doing for quite a number of years, but we think that it's progressed enough to actually talk about it. What we are attempting is actually a cross-fertilization between learning and logic. So before I start, can I get some sense of, how many of you, are familiar with mathematical logic? Okay. Well, that's very good, actually. I was not hoping that so many people will be. So what we will do is we will use ideas from logic, quite a few ideas from logic. But if you do not have background in logic, we will try to present the whole thing in the form of a few games. And those games you will be able to actually follow. So bear with us. I hope that you will get something out of it. Eric and I were preparing the talk, and we thought that just think of the number of talks that we have attended and not understood anything. So we have to do better than that. And it's probably not that difficult to do better than that. So with that background, just trying to give you a feel for where we come from. My research area is learning theory, the kind of learning theory that comes from computability theory. So we work a lot in that area to find out what are the limits of learnability in a very broad and general sense. So what we are trying to do there is, of course, not just worry about how efficiently I can actually learn a certain class of concepts, but to find out what classes of concepts are learnable in principle. Now, some of the issues that we have here are that we're not worried about batch learning as much. Batch learning is a concern for us. That is, if I give you so much data, then can you learn something from that? What we're concerned about is that the notion of induction and learning has an inherent property, and that is we cannot be sure of what we have learned. And this is opposed to the nature of deduction. So if I learn something, I always have to be aware that my current hypothesis about the reality could actually be wrong, and in the light of new data, I may have to change my mind about what I have learned. But provided, after a while, enough data has been seen, and there is a situation where no more, changing data. There could be more data, but the data is not changing the underlying concept, then I have converged to this notion that this concept has been learned. So these are the ideas that come from identification in the limit. Now, Eric's background actually is in mathematical logic. He has spent quite a few number of years trying to, battle with having models of learning in, first order logics and, looking at what's the problem there. And so a few years ago, we actually decided, let's try to find out if we can have a uniform paradigm where deduction, induction, and learning are actually part of the same paradigm. So just to give you a few more background, think of the programming language Prolog. What does Prolog do? Prolog actually allows us to answer queries of the form, there exist for all x. These are referred to in mathematical logic as sigma 1 queries. Now, this is actually a standard deduction. That is, you have enough background that forms a logic program facts, and if you give a quad, Prolog will come up with a term, a closed term, such that P of T is true. Okay? And so that's an example which is an answer to the query, there exists an X such that P of X is true. The kind of is that go deduction, kinds of queries for all X, P of X. Now this is something called induction in a way, because I look at examples and I find that P of a particular thing is true. So can I conjecture for all X, X? So in the realm of induction, and such queries in it are called pi 1 queries. Even more complicated than this are queries like exist X for all Y, P of X, Y. This query in logic is referred to as sigma 2 query because it has an alternation of quantifiers exist in for all. So it is more complex. Now, what this query says, based on the data that I have, you make a inductive step for all Y something is true, and then for that you make a deductive step that there is something that for that inductive step done is true. Now clearly, what is gained out of a logical inference is of higher quality, not quality, but it is complex, but gained out of such logical inference. What we are actually going to present to you is a logical work, a framework, queries of the form there exist for all X, for all X, P of X, and there exist X, all Y, P of X, Y can be answered. And of course, more complex queries can be answered too. But in terms of interpretation, what they mean is somewhat debatable. Now, before we actually, why would we worry about queries like there exists for all Y, P, X, Y? Think of an example on drug design. Like 1980s, when they first discovered the virus, they were very happy. And they did, them to make a vaccine AIDS virus. Found that it was really complex. The AIDS virus ought to be somewhat more complex viruses because it is not just one virus, it has lots of instantiation. You can think of them as different programs that have the same functionality, and that is the functionality of making someone HIV positive. Okay? So, think of the variable Y to range over different instantiations of the AIDS virus. Now think of the predicate P of XY to be a predicate that is true if a chemical compound X somehow disables the chemical compound Y. Disabling act can actually happen if there is certain properties between Y, certain properties between X and are true. So what happens there is when we say that Y is true, then X disables Y. Then search for a vaccine for AIDS is the answer study. There exists an X such that for Y, X disables Y. Now this is a very simplistic, hypothetical thing that I have described. The question drug design and mathematics called for identification that actually can be put in the form of sigma 2 queries. There's some motivation why would actually about learning knowledge is of this form. Okay. So what we have done is we have come up with a paradigm that includes all these things, and the way we have done it is by actually using first order. So we use first order logic and come up with a notion of logical consequence allows us to handle these kind of inferences. Now, as the restriction of first order logic to plausible logic results in the programming language which Prolog, a sort of consequence of our generalized logic is a prolonged language called rich Prolog that in addition to answering the simple things that Prolog does, can answer queries like for all X, P, X, and queries like there exists X for all Y, P of XY. And rich Prolog has actually been implemented by one of our students, actually has some connection in you. He came for the logic school last year. So he has implemented the rich Prolog and actually showed and solved certain problems in pattern languages using that just notion of Prolog. So what we are going to do is to motivate this generalized leak via a set of examples. Some of it will get slightly complicated, but I'll try to explain as possible. But after that, Eric will come after the break and talk about rich Prolog. Okay. Is there any question point? Okay. Okay, so this is joint work with Fong Nguyen and Frank Stefan. So essentially what I've said is Prolog is a programming language that implements the deductive inferential mechanism of logic. The question we are trying to ask is there a programming language that implements learning as an inferential mechanism? The second part of the talk will be devoted to this issue, and Eric will introduce rich prologue. So just a few things about logical statements. Statements are built from some rules. And what we use is the use of vocabulary S, which is a set of function symbols and predicate symbols. We also need some logical symbols, which are variables, Boolean operators, quantifiers, and possibly equality. And we will denote by script L the set of all first order S formulas. And I'll not try to go into exactly trying to build terms and things like that, but intuitively it will be clear. The example S that we will pick for this example here is actually a language with the vocabulary S, which has the constant symbol 0, a function symbol S, which is sort of like successor, and three binary predicates, pred, before, and equal to. Now, what happens in this case is we have only one constant symbol, that's 0. We can get other closed terms by using the successor symbol S of 0, S of 0, S of 0, and so on and so forth. We of course denote this by 0. We denote this by the symbol 1 bar, this by 2, this by 3, and so on and so forth. So what we are now going to try to do is actually talk about some class of underlying structures. And what we are trying to do is capture a mathematical notion called total infinite orders. Discrete. So total discrete infinite orders. Now we will use this language to describe it. Now to describe these kind of structures, what we will need is a set of axioms. So before we do that, let me try to give you some examples of what kind of structures I'm talking about. I'm talking about structures where there could be A, B, C, D, E, F, so on and so forth. So it is an infinite sequence of symbols or individual objects such that there is a minimal element A. It could also be infinite sequence of some individuals or objects like D, E, A, B, where there is a maximal element. It also mean like a two-directional infinite sequence, so A, C, D, E, F. So what we are going to talk about is these kind of underlying structure that are discrete total orders. There can also be cases, we'll see a few cases later, it could be A, B, B, C, E. So it could have a minimal element and then it could have D, E, A1, A2 and so on and so forth. So they can have a minimal element and a maximal element, but they could still be infinite. And an example, these are infinite discrete orders. This one has a maximal element, this one has no minimal element, no maximal element, this has a minimal element and a maximal element. And there are possibilities too. So these are the kind of features that we are trying to actually capture. What before will mean in this case is that given any two things, like in this say we'll say that C is before E. That will be true in that sense. Pred will be sort of like predecessor, and equal to will have a singular meaning, but that will motivate. Let us look at a set of axioms that describe this. So the first axiom is for all x is before x. What it means is before is sort of like the less than or equal to. So this is the reflexivity property. The next axiom, or the next formula here, is for all xy, x is before y and y is before x. It means that x and y are the same. So this is the entity-symmetric property. In fact, the first axiom is implied by the second. We don't need that separately. The next one basically says that for all x, y, z, if x is before y and y is before z, then x is before z, and it is the transitivity property. The next axiom is saying for all xy, if x is before y, either x is before y or y is before x. What it means is it gives a totality. That is, in this order, if you pick up any two elements, then either one of them is before the other or the other one is before the thing. So between any two elements, there is an order here. Here is a slightly interesting one. What we are trying to do here is define the notion of predecessor. So what we are saying is for all xy, x is a predecessor of y if x happens to be before y, and of course x cannot be equal to y, and also for all u such that x is before u, it means u is either equal to x or y is before u. So what it is saying is x is predecessor of y if x is before y, x is not equal to y, and the only thing between x, and there is nothing between x and y. Okay, well, that's a fairly natural notion. Then the next predicate, the next formula is for all y, there exists an x such that x is before y and x is not equal to y, implies that there exists a predecessor of, there exists an x that is a predecessor of y. What it is saying in simple terms is that for all elements, if there is something that is before this, and that element before this is not the same thing as this, then there exists a predecessor. What it means is that if it is not the minimal element, then there is discreteness to the left. Similarly, the next thing says that if something is not a maximal element and there is something that is after that, then there is discreteness to the right, that there is a sort of a successor there. And this last one basically says that there are infinitely many elements in this underlying structure. Now, this is actually infinitely many different formulas. You might wonder how you can handle in computer science infinitely many different axioms. Well, this one actually can be generated by a meta formula, or in learning what we do is if we have an infinite set of axioms, at any given time, the inference will be made based on a finite set, and the system can be provided with more and more increasing knowledge, and the inference of the system will improve as time goes by. Okay, so this is the sort of axiom set that describes this underlying notion of infinite discrete total order. Okay, hopefully things will be less complicated after this. So we denote by background knowledge the set of formulas above, BK. So BK is the sort of background knowledge, and we denote this set of formulas by that. So S formulas are true or false with respect to abstractions of realities, or with respect to the meanings we assign to the terms and to the formulas in the language. And the way we assign meaning to terms and formulas in the language is basically done by actually choosing a structure. It might be an algebraic structure, or it might be, in this case, the infinite order, and then assigning objects in the structure to different symbols in the language.
Arun?
Yeah?
Is there any specific assumption of this background knowledge, such as that it has to be a minimal set of assumptions, or, I mean, what
there is
this specific set?
There is no assumption about it being a minimal set of, in fact, it turns out that if you use a notion of, if you say that it is 1-to-1 and 0 does not have a successor, you can actually describe the infinite total discrete orders by a finite set of formulas only. So for our purpose, there is no problem there. Okay? But maybe when you implement the system, certain sets of axioms will give you better performance. Okay? But that's the kind of analysis that we are not there yet. Yeah. So given structure M and a formula phi, this is the standard logical entailment. So M entails phi, means that phi is true in the model M, or that M is a model of phi. All this is saying, if you don't understand logic, is that I have got these logical formulas that I have come up with. I assign meaning to these formulas. The meaning is assigned via a structure. We say that that structure is a model if by assigning that meaning, that formula is true. The models of the background knowledge that we have just described are structures that interpret before by an infinite discrete total order and the predecessor predicate, the predecessor relation associated with the background knowledge. There's something called Herbaland structures, and that is, in Herbaland structure, every individual interprets a unique and closed term. Now, the problem that happens is that you can actually have objects that you assign to closed terms, but the structure can have lots of different elements, and we'll see an example, which are not assigned to anything. And those structures are non-standard models. And they are the ones that create problem in some sense. But mathematicians love that because it gives a very cleaner notion of compactness. But in Herbaland structures, if you are familiar with prolog and logic programming, then they're very simple for every element in the structure, every individual that interprets a unique closed term. So here is one more definition, and then we'll probably do something. That is, we're trying to do machine learning. Now, in machine learning, what we are trying to do is this. Suppose we have a set of background knowledge T, or set of background knowledge BK. BK is the background knowledge that tells you about this particular world that you are dealing with. What I have to do is I have to find out whether a particular formula phi is true in this world. You can actually deduce, or you can, because it may not be deduced, you may have to induce it. Now, to help the machine do this, what the machine does is it has access to the background knowledge, but to the machine we also provide certain formulas in which that are, so we provide some evidence, and based on this evidence, background knowledge, the machine will tell me whether the formula is true in this mod or not. So we set up the learning process we also have to identify some set of formulas as evidential states. So the script E subset of script L and structure M are given. Script E will be the evidential state, and the structure M is something that we have chosen. Then the E diagram of M, denoted by DC sub E of M, is all those formulas in the evidence that are true in the model M. So essentially what it does is that here is a set of formulas. A model M basically divides the formulas into two parts. These are the formulas that are true in the model, and these are the formulas that are false in the model. It turns out that a subset of these formulas is the evidence. A machine only has access to these kind of formulas to make its learning inference. Then, of this inference, the formulas that are true are referred to as diagram, so DE of M. Now in this case that we have just seen, if the evidence was just the before predicate, that is all the things that were true with respect to the before predicate, then the E diagram of a Herbaland model M or BK characterizes M uniquely. Now what does this mean? Well, what this says is that if you have the knowledge of all the before things in a given structure that you have chosen, if you have the knowledge of all the before things, then if this is the kind of evidence you have, then you will be able to characterize the model completely. I'll actually come to this example a bit later when we play with a few examples. It will become let me make it a bit more concrete. So we'll play 4 games. For each game, we agree that a class W of structures called class of possible words that are models of the background knowledge are given to us. So what we are doing is a certain class of structures that assigns meanings to these formulas has been selected. Okay? We were also given a class of formulas that is the possible evidence. And we are also given a formula phi, which is the prize of the game. So the game will be set up like this. We will pick up one of these structures, and then we will provide to the machine all the formulas from the possible evidence that are true in that structure, and the machine has to find out whether phi is true in that structure or not. Okay? So this is the kind of thing that we are doing. Oh, sorry. Oh, actually I have not made the transition from...
all right.
Yeah, sorry, thanks.
I was just thinking, because you were pointing at the laptops.
I know. Yeah. Okay, so here's the game. We have a class W of structures. So that is the set of all possible concepts. Now this will actually sound familiar to people from learning theory. So the structures are the possible concepts. The set of formulas E are the data that is available to the machine. And some formula phi is the formula whose truth we want to determine. So we select one of the structures, we give to the machine all the formulas and the possible evidence that are true in that structure, and the machine has to tell me whether phi is true in that structure or not. Okay, so this is the game. So this is what we are doing here. I will choose a number M of W and provide you with the members of the diagram of M one by one. You will try and discover whether phi is true in M or not. Okay, so here W is the set of all models of background knowledge BK. So all the models are possible in this case. It could be any model, even non-standard models. What is the set of examples that you can give to the machine? Well, you can give any before, any literal with before, any literal of the form not predecessor of M of N, and you can give literals with the form M not equal to N for all Mn belonging to N. What is the formula phi? The formula phi says there exists an X such that 1 is before x and x is before 0, and 1 is not equal to x and x is not equal to 0. So what you have to find out is, does there exist an element between 1 and 0? Now remember, this 1 and 0 doesn't mean that 1 is greater than 0. You can assign to these closed terms 1 and 0 any order you feel like. So we want to find out whether the formula which says there exists something between 1 and 0 is true if this kind of data is available. You are not supposed to know that I have chosen this structure. Okay, you're not supposed to know that. So this is actually a non-standard model. It means that only the individuals, like, say 2 has been assigned here, 1 has been assigned here, but there are lots of other objects in the structure which do not have any assignment. Okay? So this is the thing that I have chosen. Clearly there is something between 1 and 0, but if you look at the data, there is no way that these things are going to actually appear in the data. In the data or the evidence that it is going to be there. But somehow, with the other data, the machine has to actually conjecture the truth. So let's play. I give you before, 1 is before 0. That's good to know. Because if there is something between 1 and 0, then it is good to know that 1 is before 0. The next example says, so when I get 1 is before 0, I do not make any conjecture. I'm just holding on to it. I have not got enough data to say yes. Next time I get 2 is not equal to 0. Well, that's good to know, but it doesn't help me. Okay? So I'm still not conjecturing the truth. Next time I get 2 is before 1. Does it help me? Remember, I'm trying to prove that there exists something between 1 and 0. So 1 being before 0 is good to know. 2 not being equal to 0, I don't care, it doesn't help me. 2 being before 1, does it help me? No. Okay. So I don't do anything there. 4 being before 2, does it help me? Yeah? Bar.
Does it represent the successor that you add in your set of action?
Yeah, it represents the successor. This represents the constant 0 in the language. This represents S of 0. And this represents S of 0.
But from your set of action, you will not deduce that 1 or 0 must be before 1 from your background knowledge.
That 0 was before 1.
Yes.
No, from the set of axioms, we cannot deduce that 0 is before 1. No, because you have the choice of choosing anything that you can say. You can put 0 to make it the maximal element. So these are just objects. You can put them any way you feel like in the order. No, you cannot deduce that from the set of axioms. No. Okay. So before 4 of 2 doesn't do anything for us. Well, next we get 0 is not equal to 1. Does it help us? Well, it is useful information. First of all we knew here was 1 was before 0, but 0 is not equal to 1 means there is a hope of finding something between 0 and 1. Next time I get 5 is not a predecessor of 6. So what? And then I get 1 is not equal to 2. So what? And then I get 1 is not a predecessor of 0. So if 1 is not a predecessor of 0, it means, and 1 is before 0, and 0 is not equal to 1, it means the machine has enough information to assume that there is something between 1 and 0. So at this point, the machine will say that the formula is yes, it is true. Okay? So what we have done here is we have selected a particular structure. This structure has assigned the closed terms in the language, has assigned these a certain order. We have access to certain examples which are of a certain form that we have actually chosen here to be. And then we are given a sentence and we have to find out whether this sentence is true or not in this language. Actually, it turns out that this is pure deduction. Okay? This is pure deduction because from the background knowledge and the evidential state E, you can deduce that this formula is true. So let's play a somewhat different game. This game, now we actually give up on all structures. We only select the Herbaland models of the background knowledge plus the sentence this, which means we are putting some extra constraints on the kind of orders that we can choose. What's the constraint? It says for all x, the successor, and the successor of x is not before 0. Okay? So for all x, now can you tell me what this means? Well, huh?
Any constant must be after 0.
Any?
Constant must be after 0.
Constants must be up to 0.
After 0.
A little more. Think about, suppose we substitute 0 for x. So what do we get here? It says s of, so 3 is not before 0.
Or the multiple of 3 on the right of 0.
Now. Okay, so if you substitute 0 here, you say, it says 3 is not before 0. Then if you substitute 1 here, it says 4 is not before 0. If you substitute 2 here, see x is for all x, so you can keep choosing different literals. Now let me explain this. This is interesting. Okay, so if I put s of s, so basically if I say for all x it is s of 0, 0, not, it means 3 is not before 0. If instead of x I put 1 here, that is s of 0, so then I get s of 0, so it says 4 is not before 0, 5 is not before 0, 6 is not before 0. So what it means is that the only instances we are looking at are the ones that allow 1 and 2 before 0. Okay? It doesn't have to be before 0. Only two things that can appear before 0 are 1 and 2. Okay? The data this time is actually simple. We don't give all the not equal to, that is actually not as written. Only thing is before mn and belongs to n. So before predicates are a data. The things that I want to find the truth of is phi, such that for all x, 2 is before x. Okay. So what I want to find out is the underlying model such that the order starts with 2. That is, everything is after 2. 2 is the minimal element. Okay. So you're not supposed to know that I have chosen this order. So 2, 1, 0, 5, 4, 3, 3 has been chosen. Okay. First I get is 3 is before 7. Does it do anything for me? It's good to know. So I don't do anything. Then I say 2 is before 0. That's good. Okay? But I don't have to make a conjecture now, because I know that the only things that can appear before 2 are 0 and 1. So I can wait. 1 is before 1. Well, thank you. It's certainly meaningless information, isn't it? 1 is before 0. Well, that's good to know. Is it? Well, it means that this is in the class, so that's good. And 2 is before 1. That is the place where we determine that this sentence is true. Why? Because we know that only 1 and 2 can be before that, before 0, and 2 is actually before 1. It means 2 has to be the minimal element. So at this point, we can make this conjecture that it is yes. So the complexity of the game is actually increasing. We will see that the previous game was straight classical deduction that can be solved by prologue. This game is sort of similar to deduction, but it is well, it is a different kind of deduction, because here deduction is like, not taking all the structures into account. We're only taking Herbaland models. Okay, so it's a different kind of deduction, restricted to only Herbaland models. You might want to think whether you can actually, let's go back there, whether this could be done for all models. Would it be possible to do something here for all models? You might want to think, and you will find that there's a problem there. Let's play the third game. This time, we take W to be the class of all Herbaland models of BK, and the evidential state is just the same as before, but this time I want to find out whether this formula phi is true or not. The game is almost the same as the previous game, except there is a problem. The problem is we do not restrict the structures to such that they had to, 0 had only 2 possible elements before it, and that was 1 and 2. Okay? So the game has changed. Now, it could be anything that we have selected, but I have to find out whether 2 is the minimal element or not. Now, in general, we cannot deduce this fact. Okay, so what we can do is we can do some sort of induction. So suppose we know that this is the case. This is the model that we have chosen. Then I get 3 is before 7. Okay. Now, does this contradict that 2 could be the minimal element? No. So I basically say yes. I say this sentence for all x is actually true. Okay? And if this is not contradicted ever by data, then this generalization will hold. But we are guaranteed that if this is not the case, we will actually be contradicted. So the next element we get is 2 is before 0. Well, that's good. 1 is before 1, that's good. So we will find that since we have assumed that 2 is the minimal element, and that's what we have selected, then we will never be contradicted, and this will actually be the case. So what we are doing in this thing is we are doing an inductive leap. We say that for all x certain things are true, provided we are guaranteed that if it is not the case, we will actually get a refutation of this thing. So this will be referred to as refutation learning, and it is the sort of inductive step that we make in logic. Let's take another game, and it's slightly more complicated. Are we having too many games? W is the set of all Herbaland models of the background knowledge plus an extra condition. Now, can you try to tell me what that extra condition is? What it is saying is that if there exists an x such that for all y, x is before y, it means that there is a minimal element, that this is something that starts here and then goes all the way to the right. If there is a minimal element, then there is no maximal element. Okay? So only those kind of structures where if there is a minimal element, there is no maximal element, or if there is no maximal element, then there is a minimal element. Okay? Are the ones that we are considering. The evidential data is exactly the same as before, and the sentence we want to now prove is somewhat more complicated. We want the truth of the sentence phi, where it says there exists an x such that for all y, x is before y. So we want to find out that there is a minimal element of the structure that we have chosen. Okay? And we'll get the data of this form. Now, suppose we have chosen this thing. Now here is the strategy or the algorithm that we will actually choose. The algorithm that we will choose is we will assume that 0 is the minimal element. Okay? If we get a contradictory fact, then we will assume that 0 is the maximal element. And if there is a contradiction to that, we will say 1 is the minimal element, and if there is a contradiction to that, we will assume that 1 is the maximal element, and then keep going. If there is a minimal element, as soon as we hit the minimal element, we will never get a contradictory data. Okay? So this is how this learning will take place. 3 goes before 7. Well, my assumption right now is that 0 is the minimal element, and 0 is the minimal element is actually not correct, but 3 before 7 does not contradict this. Okay? So I say yes. Then I get 2 is before 0. Obviously, if 2 is before 0, then 0 is not the minimal element. It means I output no and assume that 1 is the maximal element. Okay? And then I get 1 is before 0. So I had assumed that 1 was the maximal element, but it is before 0. So my thing is wrong. So what do I do now? I assume that, what do I assume? See, I had assumed here that 1 was the maximal element, and then I got the fact that 1 is actually before 0, so it means 1 is not the maximal element. So at this point I have to assume that 2 is the minimal element. So now I get 0 is before 6. Does it contradict that? It doesn't contradict that 2 is the minimal element. So I keep outputting yes, 2 is the minimal element. There exists a minimal element. 2 is before 1. It doesn't contradict. Yes. 1 is before 4. It doesn't contradict. 2 is before 5. That's perfectly fine. And so the idea is, by dovetailing between minimal and maximal and starting from, say, some ordering 0, and 0 doesn't have to be the minimal element, but we'll assume 0 is the minimal element. If it is the case, then I'll get a data and I'll continue with that hypothesis. If it is not the case, I make that the maximal element, I'll get a contradictory thing, I go to the next one. Eventually I will lock into a minimal element if a minimal element exists. Now this algorithm actually does a bit more. What it does is that if this is the case, it will converge to yes. And if it is not the case, it will converge to no. Now it doesn't have to converge to no, but machines that do this, we call them reliable learners. That is, if a statement phi is true in the model, then it tells me that it is true, but if it is not true, it can go haywire. And it is still in some sense learning, but it is not very useful. So we want reliable learners that if it is not the case that this statement is true, then it should converge to no. Okay? So what have we done? We have applied inferential mechanism that derives statements from other statements with the aim of discovering the truth. We are discovering the truth of the sentence phi from data and background knowledge. The first game is in the realm of classical logic, but not of learning. The second, third, and fourth games are in the realm of learning, but not of classical logic. The second, third, and fourth games range from easy learning to more general criteria of learning. So, let's look at logical consequence. What can we do that all these different criteria of learning and deductive inference can actually be part of a single framework like logical consequence. So what is logical consequence? Given set of formulas T and formula phi, T entails phi means that phi is true in all models of T, or that phi is a logical consequence of T. Okay, that we know from standard logic. The compactness theorem says, given theory T and formula phi such that T entails phi, then there exists a finite set D such that from D you can actually derive phi. So the idea is that if a set of formulas derives another formula, then you can derive that formula from a finite subset of that previous formula. The game of classical logic is to discover that T entails phi whenever this is the case. The first game was the particular case where E was the data that was available to us, and phi was the sentence that asked whether there exists something between 1 and 0, and so the that we were trying to solve models M of the background knowledge bk. M entails phi is true in the model M if and only if the background knowledge union all the evidential information that is true in the model proves that phi is true. So this was the game we were playing. It's standard deduction. The second, third, and fourth games are not part of classical logic because of the choice of W as a class of Herbaland structures. See, classical logic takes every model into account, every structure into account, even non-standard ones. What we are now suggesting is that we do not have to take non-standard models into account. We should restrict ourselves to Herbaland structures. And when we restrict ourselves to Herbaland structures, then we get this fine gradation where the notion of logical consequence is not the same as the notion of deduction. In fact, the notion of logical consequence can actually be generalized, and different levels of this generalization give us a generalized notion of deduction, they give us a notion of induction, they give us a notion of learning, which is induction followed by deduction. Still note how the first and second games are similar. In particular, the analog of the compactness theorem holds for the second game. But for the games beyond that, there's nothing like compactness theorem, but what we have is weaker forms of compactness. In learning, we choose W, the class of structures, which is like the class of concepts, and E, such that every model M in W is uniquely determined by its E diagram. Now, the idea here is that if your class of concepts is very complex and the data available to the learner is very weak, then you will not be able to determine the truth of sentences. So your data must be rich enough that it is able to give you enough information that you can determine what underlying model you're talking about. This condition is satisfied by the second, third, and fourth games. But it is not satisfied by the first game, and that is because the first game allows non-standard models. So, one final definition. Should we stop here or should we continue?
Actually, the tape's almost running out. Maybe it's a good
Time to stop, yeah, okay.